the down. I get out of the car. Yeah. I like it over.
That's all about efficiency.
All right, guys. Let's continue. Fun stuff today. We'll wade through a little bit more math again. This isn't a math class. I'm not really ask you to do math, but I do think it has its place. Let's see that what maybe on first inspection looks like a bunch of gobbledygook actually makes some sense. Hopefully that's the conclusion you come to and not the opposite. We'll see. Let's see what I can manage here. Yeah, we'll finish off hopefully a couple different topics and leave ourselves in good shape to then do the lab on Monday. That would be the hope. And that lab will involve, training a neural net to, learn a function which tracks some data. Okay. The most basic thing and the thing it's almost always doing under the hood anyway. Okay, so we talked about error metrics, right? So just want to get a running start at the topic today. We talked about error metrics, right? Sums of squares of error, right? That's what this picture was about. And we wrote it down as an equation. And then we said, okay, now what we want to do is we just want to do the gradient descent algorithm on that specific function. And that means for every parameter, we want to take its partial derivative, take the partial derivative of the error, and multiply by eta, move in that direction. Again, this is the delta, so this would be the change that we're going to make to that parameter every time we pass through the algorithm. Again, we've been doing this conceptually for a few days, all the way back to the continuous version of hill climbing, though there we were hill climbing, so the minus sign wasn't there. That's the big difference, okay? And of course, the real significant difference is, okay, now we know what that function actually is. It's the sum of squares of error, so we ought to be able to be much more detailed. That's the first thing on the agenda for today. Let's see what we can do in specific and detailed context, and if we can get some understanding. Let's hope so. Pick. Okay. Right. So we had this, right? Remember, that was the first step. That's just doing literally gradient descent in the sum of squares of error of our entire data set. And then we said, yeah, but the data set could be big. So instead, let's do stochastic gradient descent, where it's the same thing, except it's not an average over the data set. We're just taking one data point, doing that computation move, right? Okay. So it's getting easier. And what we want to do today is go through a couple of the two easiest examples I could come up with of a neural network, because a neural network means a collection of neurons, right? And that means one or more neurons. So I'm going to take one, because one neuron, again, like the model that in the paper that we're working with a CS PhD student on, that's a one neuron model. It's a logistic regression model. Okay, so it's not a joke to just do one neuron. And hopefully, if you can see how the math works and gets applied to one neuron, the difference is going to be that when you go and you have a deeper neural net, there's going to be more function compositions going on, right? Every layer is going to be a function of the outputs of the layer before. So instead of f of g of x, it'll be f of g of h of I of j, whatever of x, but it's still just the chain rule, okay? And then as long as you don't trip yourself up, right, which is easy to do in a complex setting, as long as you don't trip yourself up, it's just the same mechanism that you just keep applying, okay? All right, so again, yeah, chain rule, you see that here, right? We're going to need to know the derivative of the outer function and evaluate it at the same point the original expression had, times the derivative of the inner function. Yeah, so let's see. Can we do it? For real? Maybe. Okay, so the easiest case would be Bernie Widrow's, echo cancellation network, a single linear neuron. Okay, and in fact, to make it as easy as possible, I'm just going to have one input. So that means that this is the output of my one neuron, and that also happens to be the output of the entire neural network. Okay, give me an input, I'll weight it, I'll add a bias. It's linear, so I don't need an F function there. I'm done. Okay? All right. So what does it come down to? So we want to, this is actually the math you would do. After you follow this math, the next thing you could do is just start typing into Python and very quickly ought to be able to have like a working program that you could actually feed data to and have it learn from. Okay, so I'm going to write my error function here. Let's assume I have some data. Okay, and for this case, there isn't a lot of words on this slide, but obviously the x sub I, t sub i's, those are my exemplars. In other words, I'm telling the network when I give you x sub I want t sub I back out. Okay, so there we go. And I'm summing the differences between what the network is saying and what it's actually saying and what I would like to have it say. So squaring it, the sum of the squares of error, averaging it out. Okay. Pretty easy. All right. Then what I would actually be trying to put into my Python program would kind of start from here, right? The update equation for these weights. I'd start them off at some random values, and then I'd run those updates. So let's see what those updates actually are. What this says is the new value for the one weight in my neural network is the same as the old value, minus eta times the partial derivative of the error with respect to the parameter. At this point, that should be what you expect. And for the bias, it's exactly the same expression with B's instead of W's. Okay, so it's just a question, can we evaluate those derivatives or not? If we can evaluate the derivatives, all is good, and we can finish our Python program. And if we can't, we're stuck. Hopefully we're not stuck. Okay, so let's take a look. This is the hard part, so let's look at that. And the partial derivative of E with respect to W. So here's E. Okay. Now the problem, right? The problem is that the W's are not explicit in this expression, right? They're hidden inside the F. All right. So we definitely need to use the chain rule. Our outer function here is just going to be the squaring function, and the inner function is what's in here. Okay. So that being the case, okay, again, what does the chain rule tell us? It tells us that, well, let's see, maybe do I need to say more than that? Do you realize that when you take a derivative, sure, you do know, because we talked about it the other day, if there's a constant out front of your expression, that's basically inert. You just leave it alone and you pass through, and that has to do with the fact that taking a derivative is a linear operation. Are you aware that when you take a derivative of a sum, that is just the sum of the derivatives? Is that new? Not to all of you, at least, but maybe to some of you. That's also the case for the exact same reason, because it's a linear operation. It doesn't matter whether you take the derivative first and then sum, or sum the derivatives. Okay, so we're going to use both of those facts here. So I can basically, I've got a constant up front and I've got a sum up front that I'm basically going to ignore because I'm entitled to do that when I take the derivative. So those things are staying the same. Okay, and then it's chain rule, right? It's the squaring function. So the square comes down, and so I'm writing it up front to make it pretty. Okay, and then I have the original expression with the exponent dropped by 1 from 2 down to 1. That's half of what the chain rule tells me. The other half is, okay, now take the derivative of this with respect to the variable that you're interested in. In this case, it's with respect to W. Okay, so I've got a t in here. Does that depend on W? T sub I. T sub I is just a number, right? I mean, that's what the data looks like, right? It'll be the X number and then the T number, and the X number and the T number, the X number and the T. It's just a number. So there's no W's in a number. Okay, it's just a constant. Derivative of a constant is 0. Okay, these aren't trick questions. You can answer them. Okay, all right, so it's 0. So taking the derivative of that, this is 0. That's why it's left out. What am I left with? This. Cool? So that should be like 100% clear. Or if not, you can ask a question. Okay, now when I do it for B, it's the exact same expression, just with B's instead of W's for the same reasons. Okay, so all I need to do now, I've reduced this, so to do my Python code, right, I've got this for my update, but it had this in it. and this in it. And now I've got two seemingly better equations for those things, but they still got derivatives in them. Okay. So I still have a little bit more work to do, but not a lot. Okay. The partial derivative of f of x with respect to w, well, x up here. So the partial derivative with respect to w is what? It's just x. The partial derivative with respect to b, well, that's just 1. And we're done. All the derivatives are gone. It's just an equation of math. It's got a sum. You're going to have to put a loop in. You know, you're going to just type some math in. It's nothing. It's a tiny bit of code. And that would be enough to train this tiny neural network. Okay. And the principles aren't different, and hopefully we'll do one more example. It's not much more than this, but just to make it interesting, let's do another example where we're going to use ReLU activation, because that's what we're actually going to use. That's like an actual nonlinear neural network. The popular kid at this moment in time, everyone's using ReLU for everything. Probably will do the same this quarter instead of linear. And just because that last example was so simple, just to make sure you're not thrown when things start to scale up a little bit, let's have 2 inputs instead of 1. Okay, but other than that, it is still going to just be a 1 neuron neural network because because once you start nesting the chain rule across layers, it does end up to be more math for sure. It has no additional elements in it. It's just the chain rule and simplifying. That's it. You just keep doing it. You do it correctly. You will, in the end, get all the derivatives to go away and just end up with something you can put into code. And in fact, the pattern of applying the chain rule is after you do it a couple times, you will realize that's just a very repetitive process, and there's no reason why you can't write a general Python function that could basically do that work for you. And in fact, that's what you're going to get by the time we get to the lab on Monday. We'll use PyTorch. That's the dominant, that's the tool everybody's using these days for implementing neural networks. That has that functionality built in. So pretty cool. All right. Okay, so let's one more time into the gap here. We now have a squared error that looks like this. Okay, I wrote the output of the network as little o. Hopefully that doesn't bother anybody. Okay, it's got 2 inputs. Okay, this ReLU unit, so it needs 2 weights, and it also has a bias. Okay, and this time the target values are called y. Okay. The update is going to look like this. W1 after stepping 1 step through the algorithm will be its original value minus eta times the partial derivative with respect to W1. And I think, yeah, we'll just kind of follow through with W1. As you see, it's not different for W2 or B, really, and there'll just be a couple comments at the bottom about the slight differences that are there. Okay, so again, by the chain rule, we're taking the derivative of this using the chain rule. So the outer function is the squaring function. So 2 drops down. Okay, we have O minus Y. You see, thank goodness I left off all the arguments. Okay, just O minus Y here. And then we're left with partial O, partial W1, because Y, once again, will be a number that doesn't depend on W1. So its derivative is 0. Okay, all right. Now, we're going to let f be our ReLU transfer function, so we do have to deal with the transfer function. So the output of our ReLU neuron is f of s, and s is the weighted sum of the inputs, including the bias. Okay, so the chain rule then tells us that, so we want to take the partial derivative. What we need here is the one derivative remaining right now is the partial derivative of the output with respect to W1. So that should be equivalent to the partial derivative with respect to the outer function times the derivative of the inner function with respect to the parameter we want the answer with respect to. And I think I missed a partial here. Sorry. Notice that. Okay. All right, and what does that leave us with? Okay, we'll leave this alone, and partial S, partial W1, S is here. That's obviously just x1. Okay. All right. Now, the only thing left now, we're left with one additional complication we didn't face before. We now have to deal with the partial derivative of f with respect to its argument. Okay. Now, f is ReLU. So if you remember, the way to write that is just the max of 0 and s. Right? So remember. So when s is positive, great, the max is the positive number. If it's negative, then it's reduces out to the stream. Okay, and what's the slope of this thing? Well, it's just 1 over here, and it's 0 over you. So that's it. Okay, so so that's what we'd have to have some logic for in our Python code if we're implementing this. So again, so if the derivative turns out to be 0, then partial O partial W1 is 0, in which case this derivative is 0, in which case it says do nothing to W1. You should leave it alone. So we need a little if there to see, okay, if that's the case, that we're in the negative regime, then we need to just skip updating that particular parameter on this particular update. Okay. And if it's not, if we're in the positive regime, then this derivative becomes 1, and that leaves us with this as our update, right? Oh, let's see that. Oh yeah. Okay, the negative, I've just wrapped everything all together here. The negative eta is coming from here, 2 times the difference, that's down here, and the derivative is as it was in the last slide, because we're in the linear part of the ReLU function. Okay, and then the same equation works for b. The only difference is that the derivative will be 1, right? We take the derivative of this with respect to b, we get 1. Okay. Yeah, that's not a lot, but hopefully it's enough to just kind of see all these computations kind of are very samey. You know, they have the same considerations behind them. So hopefully this serves as a kind of nothing up my sleeves moment where you kind of see that, yeah, there's not really a lot going on here. You just need to take a derivative. You literally just take some derivatives and you use those to update your parameters. That's it. It's kind of the end of the story. Okay. All right. So done with all the math, but well, the derivations, but we have some thinking to do. So I want us to think a little bit about stochastic gradient descent, right? So it's clearly the gradient is clearly in there. And as we've said before, because we're not doing what the literal gradient says to do, which would involve summing over all the data, we are essentially adding in some noise. All right. We did mention that that was at least a logical possibility. It's not too typical, but it's a logical possibility. If you're just doing straight gradient descent, straight continuous hill climbing, you encounter local maxima. If we're doing hill climbing and you realize that, oh, I'm not super happy with my answer, maybe a little noise might help. Right? That's been done and will continue to be done. Okay. And we said, well, if you think noise would help, you're welcome to add some noise in. Now, the difference between that situation and this one is that if you add the noise in yourself, you can make sure the noise property are whatever you consider reasonable. Gaussian noise, put Gaussian in. If you want noise that's uniform over an interval, go to town, right? You would provide the random noise. And now we're not adding it in ourselves, so we do not have control over its characteristics. Not its variance, and not other aspects of the distribution, though it's going to be zero mean. That's for sure. Okay. So at the end of the day, the stochastic version of the algorithm has some things to say about it, and I wanted to kind of lasso them all into a bundle here. First, obvious thing, right? You don't have to sum over the entire database to take a step. Okay. There certainly are situations where you might never even need to touch every bit of data in your database. If your database is really, really huge and your problem's really, really easy, with stochastic gradient descent, you'll be converged long before you get to the end of the database. It just kind of, that's not real typical, okay? But this just decouples two considerations that really don't have much to do with one another. One is how much data you have, and the other one is how fast is your algorithm at taking steps. You're going to need to take a bunch of steps to converge with this. Even in trivial problems, you need to take a lot of steps. So it matters. That's it. Okay. Second point here is, okay, we didn't get to pick the noise, but just logically, it might help you avoid local minima. And in fact, people find that in practice, it does help. It helps often enough that that's still a thing like that. Okay. So not only is it faster, but the fact that it's noisy might also be helping me. Okay. And last, but this doesn't apply very often. And if you were actually trying to do live learning on a stream of data, the whole framework of we'll get the whole database and then sum over the whole thing. There is no whole database. I mean, it's changing moment by moment. Okay, so you hardly have a choice in this setting. So I don't know how convincing you find that, but at the end of the day, it's pretty rare that people do actual gradient descent. They will do mini batch gradient descent. Remember, instead of one sample, you take 10 samples or 100 samples or some small number, maybe 1,000, and use that to compute the gradient. If you're thinking things are too noisy.
How often is it that your ability to control the characteristics of variation of the noise your algorithm based the positive effect on?
It's impossible to say because that idea that you can add noise to continuous hill climbing in other settings, it's true, but I just don't know a lot of examples for that. I bet there is literature for it if I really wanted to go and look. But here we're talking about a technique that's literally used like everywhere in the world that's doing anything AI versus something that's an exotic piece that maybe a couple people have touched. So I don't know. I couldn't say. Other questions? All right. So I kind of really need to merge these together. But this is this list of problems of stochastic gradient descent. You should recognize it because it's the same ones we talked about when we were talking about continuous hill climb. Okay, just with instead of maxima, we've got the problem of local minima instead of local maxima. Okay? It means the same thing. Plateaus are still the same thing. Of course, it's kind of an inverted plateau you're liable to see when you're doing gradient descent. Narrow valleys, it's bouncing back and forth, not making good progress toward the solution, still there. A plateau, again, is a flat region. So once again, you're going to have difficulty making progress toward the solution. Those are going to be issues. And now I've just added one more in. So the distinction, these are almost the same thing, but they're not the same thing. So please, you want to know these for the test. Right. Now, instability is where things are literally blowing up to not a number. Remember the picture I had? So if you go and do the math, take a parabola, locate yourself here, compute the gradient, right? And then make it big enough, and you'll see that you can bounce further away from the zero than you started. And if that's the case, because the gradient's properties are kind of quasi-static here, you'll bounce even further away here, and further away, and further away, and eventually you end up with not a number or a weight or bias in your network, which is not very helpful when you need something to actually compute with. Okay? And, actual minima are not literally parabolas, but, there's a thing called a Taylor expansion, right, for functions. So every function is approximately a parabola about its minimum. So the fact that you see this effect on parabolas, you might be inclined to think, yeah, maybe you actually see that with legit minima and real problems, and you totally do. You need to make sure your learning rate is small enough. And the other thing, and this is the new piece here, what's the difference with non-convergence? Non-convergence just means that if you imagine my learning rate was not so big that it bounced me further away, but it bounces me about the same distance away. That's non-convergence. I'll just end up doing this, bouncing back and forth from side to side. Okay. And this is also something that does happen. And we will see a lecture or two later by the end of next week that there are some automated techniques that try to grapple with this well enough that a lot of people, including me, use them. There's still that. There's still hope for dealing with some of these things. And I would do ask on the test some general things. So hopefully it's some picture about these problems, and also by the time we're done, what you can do about them.
For training neural network, your data, like the step that you're taking,
Yeah.
is not a constant in both some.
Yeah.
So kind of for non-convergence, if you run into a situation where it realizes you're doing that, I think you just reduce or increase data.
Well, and it's often what you end up doing, but what does that mean? It means you kill your original trial and you recode and you run again. Yeah, that's one of the things you can do. And the fancier things are techniques where you try to detect and adjust live while you're still running without killing and restarting. And they, yeah, like I said, that was what I was referring to with my comment, that, oh, they work well enough that people use them, including me. But there's no guarantees that come with them. They probably also hurt you some number of times too. And you'll never know unless you're doing very, very detailed and systematic experimentation, which no one is these days, because it's hard enough to train the neural net in the first place. And you're experimenting with your application. You don't want to experiment with basics of neural networks. So, all right. Okay, I'm going to move on. Okay, so this is the last topic for today, but it's kind of a big one. Okay, so let me ask you a question. Back in time, well, when I was a little graduate student, the Navy came up with this data set that I'm telling you about that we've actually it's still there out on the web. I've still used it, detecting rocks from cylindrical objects, which might be mines. Okay, and it had, I don't know, a couple hundred examples. I mean, it was a field test. They actually went and got sonograms out in the field to populate this data. Okay. So what I want to ask you is, so let's say I take that data, I do the stuff that we've been talking about up till now. I do it really, really well, and my system totally nails, like, it's a sonar spectrum. It's the return of the sonar spectrum. You break it up by frequency bands, and it becomes just a series of numbers that go into your neural network as an input. That's it. And then the output is just 0 or 1. Is it a rock or not? Okay. My system nails it. It totally nails it. Okay. Is that going to necessarily please a Navy operational command when I come with my thing? It totally nails the data set. So that answers all questions, Andy?
I think it would get you in the door to try it out in broader applications.
Oh, okay.
But that doesn't necessarily mean that your testing will then carry over to the field and get you.
Right. That's the issue. Generalization, right? Just because you can do well on some fixed data set, in almost every case, I can think of a couple of exceptions I've seen in over decades, but in almost every case, that's not what anybody really cared about. What they care about, that data was drawn from some data distribution, some world of data that no one has their hands around because it's it's infinite or nearly infinite. Okay. And you have some little part of it, and you're saying, oh, I do good in this part. And what people really want is something that does well on the world of data that's out there. Right. And
something in much less sophisticated ways when you're doing regression things, we're doing data analysis.
Yes.
You'll sometimes keep holdout data.
Yeah.
Like I would make a model and then.
And so are we. And big time. Yeah. Stay tuned. Yeah. Maybe a couple times. Okay. So yes, this is the same issue. So hopefully you guys have a good foundation. This is easy for you. But this is certainly something which is relevant to the lab. Because you know what? I'm going to give you a sample of data from a data generator. I'm not going to give you the data generator, and I'm not going to give you the data I'm going to actually test the system on. So you will have no way of knowing exactly how your system will perform when in my hands. Okay, so so hopefully that whets your appetite for information about techniques that will help you to do well under those circumstances. So what can you possibly do? Okay, it's a tricky subject, and it took quite a while for the field in early years of neural network research, the latest resurgent, the late 80s, 90s. Took many years for the field to kind of get their hands around this to realize what needed to be done. And there's a lot more. It's a broad and deep area. I'm just going to try to keep it to useful basics. Okay. Right. So we need to perform well on future data, not just the training set. Okay, that's what we said. Okay, next point. You are aware, because there was a slide about that, this universal approximation capability of neural nets. We know that neural nets are capable of fitting any data that you give it. And I sold that as a good thing. And we often think about it as a good thing. However, because they can fit anything, they can also fit the noise in your data, right? So you have a messy data set like this. Now, I'm not sure, when I look at this, again, you can't be 100%. I don't want to give you the idea that, oh, you could just look at it and be 100% confident. You can't really. Okay, maybe this is actually generated by a linear function here, and we were just unlucky. It's just an unlucky series of draws from the data. Okay, it made it look like it's bent, but to my eye, it really looks bent. Okay, so to me, I'm pretty happy with this, but I'm not at all happy with something that tries to go and hit every one of the data points, right? And this would be the one when I said, oh, I totally nailed the data. It's actually can be a bad thing. If you know there's noise in the data and someone's like, my errors are zero. It's like, okay, there's like no chance that's actually a good system. Okay, what we want to do is kind of split the differences, right, in a smart way. Okay, now when you do this thing we don't want, this has a bunch of different names and they all mean the same thing. Some people call it overtraining, like you should have stopped earlier, because generally the system will start with a rough shape and get more refined. So the mentality here is you should have stopped earlier. You did too much, right? Or overfitting, you're fitting more than actual data, right? Or sometimes just fitting the noise, which is maybe the most explicit and clearest description of what's going wrong here. Okay. All right. So the essential point I'm saying here, maybe it's just an essential point, but the essential point to understand, certainly it's an essential point at least, is that when you measure the error of your function, right? If I go through and measure my sums of squares of error for all these cases, let's say, whatever that number is, it tends to be, it's always biased and often is highly biased in an optimistic sense. And if what you care about is future performance on the whole world of data. Because, I've taken my tool and I've tried to hammer it as best I could to fit the data from the little sample I pulled out of the world of data, right? So it should make some sense to you that, well, of course I'm going to get a good answer on the data that was in my hands, right? And I built the whole system around that data. So this should be, I think, is a non-controversial thing to say, right? I'm going to be biased, and I'm going to be biased in a particular direction. In other words, I'm going to make it look a lot better than it's probably going to be when I go out to the whole world of data or to a second sample from that world. That make sense to everybody? All right. Yeah, so if you're in rare situations where you have an infinite stream of training data coming in, and you're continuously training on that training data, a lot of times in these rare instances, you don't have to worry about generalization, but that's really rare. Most of us are not normally going to be in that situation. And you won't be in lab 2. Okay. So let's talk about estimating performance. This is the holdout idea comes to the fore here, right? So the right way to estimate future performance, right? You get all done, you're going to be trying to minimize the error on your training set. I mean, what option do you have? We're doing gradient descent. We are literally trying to, if you like, bias ourselves on that data. Because the data is all we know about the world, from the point of view of the immediate exercise. So there's no way we can really avoid that, completely avoid that kind of bias. There are some mitigating things we can do beyond what's on the slide. Okay. But what we really need is a held out set. And here it's being called the test set, some data that has not been used for training in any way. Okay. And there's a kind of a slippery slope. People tend to want to use the test set early. I mean, so, well, I have quite a bit. I think I have more to say about that. Actually, just on the slide. So let me just kind of go down point by point.
The training set, a test set, and a validation set. Well, like they split the data into 3 chunks.
Yeah. We're going there. We're going there. Yeah, that's what I would consider good practice, and what I'll encourage you guys to do for that too.
Because even if you avoid, testing against the test set iteratively as you go, you're still probably going to test against the test set before you're done training algorithm.
Well,
So like, what do
yeah,
you do if
it depends on technique. Yeah. So that's what I'm trying to cover here. So let's give me a few slides, and we can double back and discuss. Yeah, and certainly what I'm saying here isn't the be all and end all either. But okay, so right, so the notion here is that you're given this block of data, these sonar returns. It's not trivial to go get more. Someone went out in the field with equipment and measured those things under certain circumstances. It's not going to be easy to give you more. How are you going to use that precious data? And what's suggested here is, maybe if you're required to go back to your sponsor and tell them how well the system is likely to perform on the world of data that they care about, if you're required to do that, which you should be required to do, then you really need to put away some of that precious data right on day one, never look at it, leave it on the side until you're completely done building your neural network out, training it the best you know how, and only as the last thing you do before the system goes out the door is to open that held out data and measure performance on that data. If you do that, the number that you get, there's no guarantees associated with it, but it will be an unbiased estimator of its future performance. And to the extent that you didn't, and you were going to do that, but then when you open the test data, you realize your system was terrible and you needed to restart. Okay, then you're already getting information out of that test set. Okay, and it is a slippery slope from constantly using that held out set. That's very, very bad too. Well, I just peeked at it a time or two. Okay, that's less bad, but still could be an issue. All right. Okay. Yeah. General rule is this: the more you've used that held out set, the more biased that estimate is going to be from that set. So best to avoid touching it completely. Okay. Yeah. And in particular, you want to avoid constantly looking at it would be the worst case. Okay, I think we're beating it to death now. So I'll move on unless there are questions. All right. So I want you to I think it's a little counterintuitive. What is the harm of peeking a little peek at my test set? And there might be little harm of one little peek, but to understand why just looking at the test set at all could hurt you, and I have a little thought experiment. This is an extreme peeking example, but it give you the thinking behind it. Okay, so consider the following. So we want our neural network on our sonar returns. We definitely want it to generalize. We want it to do well on the world of data, not just the little data set that we have. That's our main goal. Okay, so can we agree? We can agree, I say. Can we agree that if the way I'm going to train my neural net is to not do any of the stuff that I'm teaching you, I'm just going to randomize the parameters. That's it. Just going to draw them from a random number generator, right? Now, this seems like it's probably not going to accomplish the goal of doing well in the world of data, but it's not. I'm going to do a little more than that. I'm not just going to randomize it once. What I'm going to do is I'm going to randomize the neural net. Then I'm going to peek at the test set and look at the performance. And I'm going to randomize it again and peak. Okay. I'm not saying this is practical. Is it possible that by just randomizing the weights, I could peak and actually get a good score?
Yes.
Okay. Is it likely if I have unlimited time or maybe a very small data set that I will get in that situation, that I will have a random net that gets a good score?
Yep.
It's a certainty. As long as there are good parameters out there to be found and I randomly sample, eventually I'm going to get in the neighborhood of those parameters. It's a dead certainty. So you know that this is extreme, right? No one's actually going to do this. But the extreme case of just peaking, well, I didn't actually train on the test data. I just peaked at what the performance was on that data. I didn't take gradients of it. I didn't use it in a material way to benefit the system. I just looked at the performance with it. It can still kill you. That's the point. Okay. So, yeah. Questions on it? I hope it makes some sense. If you go and it took a long time for the AI field to realize what was going on here, and there were a lot of bona fide statisticians who were involved in doing the research for this, and they proved a lot of theorems. But in the end of the day, I believe this is the phenomenon that it comes down to. So you want to dig into it with tons of math and really, really deep papers. They are out there to be read. But I think if you understand this, you're good.
This is probably an obvious statement, but before you field an AI, you're locking all your weights. So if you were to do that, then could run your test data through it a million times. And you.
Oh yeah. If you're not going to actually go and change the weights, that's not.
If you lock the weights, then you could run it as long as you haven't used your test data, help train it.
The problem is when you go back into the lab and rebuild the system.
Yeah.
The main point here is just that it's not what people are told is bad and what kind of everyone knows is bad is to actually go and train on that test data. Do the same stuff with the test data you did with the rest of your data set. Follow the gradient and make sure you're doing well on it. Okay, everyone kind of knows that's bad, but the point here is no, just looking at it can be bad. That's the point. All right. All right. So, detecting generalization problems. Right. So given the way I said it, how can we avoid this issue that you go and you create your neural net and then you're going to do everything right. So you're not peaking, but just on the way out the door, you do one test on the test set and you realize the number is terrible and the system's going to look unusable. Whatever the reality is, it looks unusable. How can you avoid getting into that situation? So there's a couple things to say about that. On some occasions, like for example, with the sonar, I mean, you could go back to the Navy that gave you the data and say, hey, those power readings in each one of those frequency bands of the sonar returns, like what's the actual accuracy of those power values? And they would be able to tell you that. Okay. So sometimes we kind of know what how much of the fuzz in the data is actually noise for sure, because someone tells us, I know the equipment that was used to gather it, and it's only good to yay big. So anything that looks like, oh, looks like there's a little wave going on that's smaller than yay big, that's noise. Don't bother fitting it. Okay, sometimes you know that, and that would be the best thing. Okay, but in general, you don't. And the thing I would suggest is, as was already came out in the discussion, you can hold out an additional test set. You take your one test set out at the beginning that you're going to use at the very last minute, and from the remaining data, you take out a second test set. Now, this is painful when you don't have much data to start with. And when data is expensive and you have to go to a test range and it like costs money, you're actually like firing a weapon or you're doing something that costs money. This is painful. But I don't have a better thing to offer to you. And then the idea is that you use this where you would have gone and peaked at the held out test set, but you know you shouldn't, and you're determined to do things the right way. Now you'll peak at the second held out test set, which is specifically there for the purpose of peaking at. Okay, but the same considerations apply. If you peek at it too much, you ruin its helpfulness in guiding your construction of your original neural net. So your goal should still be to peek at it as little as you can. But at least now, when I've got my two test sets, right? If I go and I build it, looks like training value looks good. I test with the first test set and it confirms that it's good. Okay, then we're fine. I do the second test and I send it out the door. But if that first test says, no, you failed, whatever you did, you made some bad choices. Okay, now I'm not dead. I didn't waste the final test set. It's still waiting for me before I go out the door. I can go and throw all my work away, start from scratch if I need to, and it's still all cool. I will still get an unbiased estimate on my final performance when I'm done.
When you're dealing with limited data,
Yeah.
how big should your test sets be in comparison to your training sets?
Yeah, there's no good answer to that. People divide up evenly. And usually when data is expensive, people do not divide up evenly because it's just so, if a problem's really hard and you don't have that much data, like you're gonna fail training neural net unless you use most of that data for training. So they will make those two held out sets as small as they dare. But I don't know any even good rules of thumb for that. I'm pretty sure you could build examples where, but any rule of thumb I give you would fall on its face. So you're gonna have to take your chances with that. All right. Okay. Now there are multiple ways we can fix generalization problems. Okay, so let's say we're seeing from our first held out set that we have an issue. What can we do? Okay, there's a number of things. These are all things that I've seen used effectively. The most basic thing is just take some neurons out of your architecture. However many you decided to put in your layers, take some out. Because every neuron lets the function kind of wiggle a little bit more, just kind of intuitively speaking, right? Clearly. I mean, if you just have the one neuron, what can it be? It's going to look just like a ReLU on the output, right? It doesn't have hardly any flexibility at all. It's only when you add these things together more and more and more that it becomes able to learn the noise or what have you. So take neurons out. There's a notion of weight decay, which I'll show you. So the idea there is you build into the algorithm that you have something that's going to favor small weights as opposed to large ones. So you didn't completely remove any neurons if you use weight decay, but you're limiting all the ones you have. You're kind of putting the parameters on a leash so they have a harder time, making very bendy functions intuitively. I think that's good enough for now. Hopefully that makes some sense. And last but not least, this is still a favorite, doing early stopping, right? Remember I said overtraining. So one thing you could think about is maybe you could have stopped the training early. So what you do with early stopping is, as you're training at regular intervals, you go to your first held out test set, not the final one. This is often called in this context a stop set, because it's there specifically to tell you when to stop training. And you look at your performance on that stop set. And what you typically see is, well, you start off with a network which is random. Okay, so it's doing terrible on both the training data and the stop set. Okay, then it's going better on the training data and also better on the stop set. Usually not as good because, it's not able to train on this data. Okay, and after a while, you will see it turn a corner where the performance on the training data continues getting better because it will all the way down to, if you've got a strong enough neural net, it will like literally fit all the data perfectly. But the stops data says, getting worse, getting worse, getting worse. Okay, and now you can use that as a signal to stop your training. Okay, and there are plenty of other approaches. Okay, we're almost out of time. Okay, good. And this is, and we're at the perfect place to stop. I'll talk about the details of the algorithm, some of these special tricks and some other stuff when we get to our next lecture day, maybe Tuesday or later next week. Okay. All right.
Can you release the lab today, even though not there? Just so that
I'd rather not, because I want to talk over it, and you should not want me to either, because my labs are pretty terse, and I think it helps to also you don't want to get one impression from my written thing, and then after a week of work realize that, oh well.
But if I promise not to do that.
No, not gonna be good. But Yeah, it'll be soon. Well, gee, if I knew people were that anxious, I might have like dashed ahead to try to make sure we got the lab out before the weekend.
We had a lot of work this week and preferable to avoid it. Started this week, it's pretty good for that.
Oh, is that right? Yeah, you have a lot coming up this week.
No, this past week.
Oh, you had a lot this past week. But we are going to have 2 weeks for the lab, by the way. So I mean, it's not going to be a super rush. Actually, you ought to be able to get it done. Yeah.
Lieutenant Colonel Morris has been talking to some of the thesis topics.
Yeah.
And some of the thesis topics that are coming from the Neller Center and the Marine Corps Warfighting Laboratory specifically from Scotty Platt. Are pretty AI themed. Have you looked into any of those topics? Do you have any opinions on those topics?
Yeah, I don't know. I'll have to ask him.
I'd be interested in hearing your opinions on some of the topics that they're.
Well, I mean, my whole thing is trying to build some AIs that they could use in the Miller system. So I'm probably not going to be against anything here. I talk to Scotty all the time, including this morning. So hopefully I'm pretty synced with the kind of stuff he has there. And we do have a couple of platforms that the MCU cares about, and because they've been putting money into actually preparing these platforms for AI use, I think they're a little ahead. You know, the Neller Center right at the moment is in a weird point. You know,
People keep telling me.
they had this whole project called Pioneer, which was supposed to be their whole software platform for doing wargaming. They were really unhappy after a year or two in, and they totally pulled the plug on that. And Scotty's been one of the people like scrambling around trying to find. So like at this moment, I know what the plan is there. But I'm not sure they have a feasible plan.
The reason I brought them up is because they seem to be the external, like, location that is asking for thesis projects that are AI.
Yeah.
And I think it is a cool topic, and I wouldn't mind doing something like that, but I was hoping to acquire a thesis topic before the end of this. And so I've
got software
kind of
sitting
coming
around.
back to see if it'd be available to talk in the near future. I know Hunter is actually going to talk to him next week. But if there was any kind of discussion about, hey, this is kind of where things are going and it's what we're thinking, I wanted to make sure that I tie you in.
Yeah, please do. I mean, again, I'm talking to I'll see what Matt's been saying because but I talk to Scotty all the time, and yeah, if I'm not averse to changing course on the basis of, you know, and if we're getting any smarter, if someone's gotten smarter than I am about what the Nellis Center is likely to need. And like I said, some of the software right now, actually, MCU is doing a lot of driving the discussion because their needs are kind of less serious. I mean, they're doing PME with their games. So they like actually have games that they know are useful for PME. Like they have, unlike the Neller Center, where it's unclear what the actual software is that they're going to actually use. They kind of know what the software is. It just doesn't have the AI that they want. So that's kind of been my initial vector going into this year, but I'm not averse. I mean, I've been tracking so what did, I'll have to find out. I mean, you made me really curious what Matt was showing, and I wonder if it's stuff I've seen or not.
I don't think
hope so.
It's any kind of secret. I could
Yeah.
probably send you the thesis topics or at least a thesis overview because
Yeah.
the overviews are all very broad.
Yeah,
It's
yeah.
not like a specific problem that you could tackle as a thesis problem.
Yeah.
It's more like subject areas. And so I was hoping to ask Lieutenant Colonel Black, you know, to help me narrow something in. Because
Yeah.
I can narrow it in myself, but I'd be going in more or less a random direction.
Yeah. No, let's do it together because I'm pretty determined to support those efforts. Like I said, it's just that it's been surprising how much easier it is to have discussions with MCU because they actually know what they at least think they know what they need. And with the Neller Center, it's like, you know, it looks like they maybe want to use Command PE like short term, but that's just stopgap. I guess they're already have decided that that's not going to be the long-term solution. Well, what is? Well, there's this thing called War Matrix that the Air Force has been developing that, I mean, that might, they think that could actually be a mainstay for the Neller Center, but where is it? Well, it's being created. And I know a lot of the company that's involved with building that thing is Code Metal, and I have been tracking very closely. They've been trying to run a public war game AI contest this year, which I thought I would also recruit students to participate in, but I haven't because they've been messing it up. You know, they just have not been serious. And so if I hope what's going on is they're not serious with the public contest because they're really doing a great job for the Air Force and Marine Corps. But if that's not the case, then they're going to be on to Plan C shortly because they won't come up with something useful. So yeah, let me send me the slides. I'll also ask Matt. So I'll, you know, I'm sure Matt's happy to give me whatever he's got, and certainly talk to Scotty, and but come back around and talk to me because probably I'm your best resource for advising on that vector.
Did notice that you've been a thesis advisor for pretty much every AI thesis that's happened in the last
Well,
years.
Well, that's yeah. Though that's changing because AI is becoming like everybody needs to do AI. So Rob Fusco.
I do. I actually was gonna ask you about that as well, not
Yeah.
specifically about him, but he sent out an email the other day saying that there was some sort of 4-man AI theme project that he was putting together and wants to talk to people about on Monday. I don't know if we looped you into that. I can forward
No.
you that email as well.
Yeah, I wouldn't mind. Yeah, but he's doing interesting stuff. He's working with Charlie